Okay, so for today, we're focusing on this sheet. It's the bottom file in today's folder, and it is the Identities Sheet. You will get this exact sheet on the test day. All right, I'm going to help you understand. I showed you exactly where this came from with the triangle and the a squared plus b squared equals c squared, but not going to rehash all of that. I do want to remind you, though, that you usually don't see them quite this simple. You'll usually see in the middle of a problem, you'll have like secant minus 1. And you have to be smart enough to go, oh, that's this one, except they move the 1 over there. So what could you replace secant squared minus 1 with? Say it if you know it. Tangent squared. Do you want to make a list of all the things that are, rearrangements of the originals? Probably not. It would take you a long time. And besides, we're not going to let you bring your own sheet into the test. So, I'm actually, for the first time, seeing what some of you guys' faces look like. What a concept. All right, so anyway, I would recommend that you take this and rearrange each one just like in your head and go, what if I move the 1 over here? Could you also move the cotangent squared over there? Yeah, this would be 1 equals cosecant minus cotangent. All right. So 1 could be 2 different things. 1 could be this. 1 could be this. And would you make the last thing that 1 could be equal to? Now, if you just see a 1 in a problem, you can replace it with this, or what else? All right, you'll need a neighbor to compare with here. I'm asking you to tell me what's one more thing 1 is equal to. So I'm going to assign you partner. Okay, so the last one was this one right here. And if you arrange it to make the 1 be alone, you would grab this tangent and move it over. So it'd be secant squared minus tangent squared. Raise your hand if you had that one right. Okay, you caught on to the pattern of what I was going for there. All right, we've talked about these a gajillion times. Whenever you see these, like 1 over cosecant, it's just begging you to swap it out for sine. And you need to know which ones go with which, right? It, of course, can go backwards, like cosecant can be here, and sine can be the thing that's flipped. So, all right. I hope you also get that these all can be squared. So that this could be squared and this could be squared, and they'll all still work if they're squared. Any questions about those? All right. What's special about this is I said it would probably come up more than any other single identity. It's just tangent being sine over cosine just comes up a lot. It's partially because one of the big strategies you should know is make everything into sines and cosines. So if you've got a problem, a lot of times you can solve it by making everything into sines and cosines. You might be like, well, but what about sine? Well, that is sine. What about cosine? It is cosine. What about secant? Well, that's 1 over cosine. So everything can be made into sines and cosines. Cotangent, cosine over sine. It's just a flip. All right, so those are special because they come up a lot. These will come up now and then. Whenever you see a negative sign, that's sine of the opposite of the angle. All right. I'm going to try to just show you an example quick, and if you don't understand why these work, it's okay. But for the people that really want to know why, I want to show you briefly why these work. Okay, so let's look at, for instance, this scenario. Would you all figure out for me in quadrant 1, if this is the 1, 2, square root of 3 triangle, would you figure out what that angle is? This is not a trick question. It's supposed to be pretty easy. Okay. Sine of that angle would be 1/2. What's cosine of that angle? Square root of 3 over 2. Did you get that one right? Okay, good. What's tangent of that angle? TOA, opposite over adjacent, is 1 over root 3. You getting these? These are ones we've done before. Nothing new here. Okay, but what if I do the negative of that angle? Do you get that angle must have been 30 degrees, aka pi over 6, right? But if I do negative 30 degrees, do you get I'm down here? And I still can do 1, 2, square root of 3, but something's different. What's different? The 1 is negative now. And so now this angle isn't 30, it's negative 30. Could you also say it's 330? Yeah, those are all coterminal, but it's sine of negative the angle would be doing it this. And that's like the opposite answer. Why? Because sine down here is now negative 1/2 over 2. So sine of the negative angle, negative theta, came out to the opposite of what it was, negative 1/2. But cosine of the negative angle is exactly the same. Why would cosine of negative theta be exactly the same? Because it's adjacent over hypotenuse. And look, neither one of those two is negative. See? So cosine of a negative angle is just the same as cosine of the regular angle. They are the same. Does that make sense to you? So a few of you might have caught that. And if you didn't, it's okay. From now on, you can use these identities because they are facts that have been proven. And that means, like in a typical question, let's say you see this in a typical question. You see a negative of sine of x. You can be like, oh, I can replace that with this, sine of negative x. Or maybe you have secant of negative x in a problem. Oh, I can replace that with regular secant. All right. Next up is the cofunctions. I am going to, with a highlighter, cross this off, meaning you could use it, but we don't use them very often. But I want to tell you something about it at least. And I'm not saying we'll never use this, but this is kind of a cool relationship that at least at some point you should understand. If I said sine of 30, can anybody tell me what this is trying to say? Sine of 30 would be equal to cosine of, what's the relationship between this and this? One of them is 90 minus that, and the other one's that. So they both add up to 90. So sine of 30 is equal to cosine of 60. I don't know if you've ever noticed that if you do sine of the 30-degree angle, it's the same as cosine of the 60-degree angle. I'm going to show you that in a triangle. Here's your 30, 60, 90 triangle. And I got a 1, 2, and a square root of 3. What if I asked you for sine of 30? Do you get how that would be? Sine of the 30 would be the opposite over the hypotenuse. Do you get how that would be the exact same thing as cosine of 60? Cosine of 60 would still be 1/2, wouldn't it? So this is just an official way down here, the official way to say that these two angles, let me highlight them. Come on. Here and here, when you add those together, you get pi over 2. They add up to 90. If you're really getting this, then you should be able to tell me this. What's the tangent of 60 equal to? Look at this one here. What would tangent of 60 be equal to? Remember what happened last time? These two add up to 90. So I hope there was somebody out there who was thinking cotangent. Notice the cofunction of 30. Good. Who was thinking cotangent of 30 but not saying it? All right. We'll try one more. What if I said, if I had the secant of 50 degrees, that'd be the same as, there we go, some kids are catching on, cosecant of 40. Notice all of these are co-functions. Secant, cosecant. Tangent, cotangent. Sine, cosine. So from now on, if I said, hey, I got tangent of 20 and I have no clue what to do with it, you should be able to go, well, it's the same exact thing as cotangent of 70. Because, you know, these two add up to 90. Raise your hand if you understand that. Okay, good. Then if you really do, what's the sine of 10 degrees equal to? Check with the kid next to you and see if they have the same thing as you. All right. Cosine of 80. These two will always add up. Yes. Come back soon. These add up to 90, and they're co-functions. Sine, cosine. What goes with tangent? Cotangent. What goes with secant? Cosecant. All right, so I think we've got those. So if you ever saw one of these in a problem, like this right here, you could replace it with that. And boy, that would be a lot simpler, wouldn't it? Okay, next. These are just saying that if you add 2 pi, you're going to get the same exact answer as you would have gotten in the first place? Because adding 2 pi just puts you in the exact same spot on the unit circle. You know what I mean? So let's say you were about to do this problem here, and you had a triangle drawn, and it was 30 degrees, and you were about to like get some answers, and then somebody said, no. I don't want 30. I want 390. You'd be like, it's the same exact place. So the answer is exactly the same. So if I'd asked you for the sine of 30, that'd be the exact same thing as asking you for the sine of 30 plus 2 pi, which is like 360. So sine of 390, it's the exact same thing. Either way, sine of 30 is 1/2. So sine of 390 is also 1/2. I just added 2 pi to it and I get the same answer. Does that make sense? Those are pretty easy. Weirdly, with tangent, it's different. Why? Because with tangent and cotangent, you'll see when you are better at graphing them, when you see the graphs of them, that their period is different. Okay, so you only have to add pi and you'll get the exact same answer. Here, adding 360 just kind of makes sense. You can go like, well, you want me to add 360? Well, I'm going to go all the way around and I'll be back in the same place as I was. But it's a lot harder to explain why for tangent and cotangent you only add pi and you get the same answer. All right, let's just do one like that. Let's say I had tangent at this spot. Would you agree that spot is 1, 0 if I'm on the unit circle? Make sense so far? What is the tangent at that spot then? 0 over 1, which equals 0. So tangent of 0 degrees is equal to 0. And they just said that if I go over pi, which is over there, I should get the same exact answer. We'll see if they're right. It's -1, 0. What happens? Tangent y over x, 0 over negative 1. It's still 0. See how we added pi and got the same exact answer? Okay. All right. Then we have these ones, and these come up a lot. I'm going to tell you, you need to know these more than you need to know the ones I just described. But for these, I'm going to save you the pain of learning exactly where they came from. It's kind of complicated, and it would eat up all the rest of our time. And I don't want to do that. So I'm going to highlight a couple for you that I feel like come up the most. That one comes up a lot. And this one comes up a lot. And I'm not going to highlight what this is equal to because you get to pick. You could either replace it with this or this or this. You get to pick whichever one feels better for that problem. So if you're in the middle of a problem and there's a cosine of 2x there, you can pull it out and put in any one of those three. All right. If there's a sine of 2x, this one, they actually recommend you memorize that one. Why? Because the AP test does not give you formulas. You have to memorize certain things. And on the AP calc test, sine of 2x comes a lot. And it's pretty easy. 2 sine, cosine. I don't think they're going to make you memorize cosine of 2x. I guess I don't know that for sure, but I have been told by calc teachers that one comes up, make them memorize that one. Okay? So if I were you, I'd handwrite it out because it'll increase the chances that you will remember that one. Sine of 2x is 2 sine cosine. Almost kind of rhymes a little bit. And if I ever saw the sine of a couple angles being added together, like this, that would be a hint that I must be in this one of those sum or difference ones, and they're really long. Look at how long that is. We may spend more time on a problem like that later, but for right now, just know that these are identities, meaning if you ever see the one, you can swap it out for the other side. Like those two blue things right here, that if you saw that, you could replace it with that. Okay, so we've covered all the things on the sheet now. Anything on here, you can swap, and you'll have this sheet. So it'll be fine to, in the middle of the test, if you ever see this, you can replace it with that. If you ever see this, you can replace it with all that. And I think it's a really good time for us to practice these. So I'm going to give you and your partner some time. We'll start with easy ones, and then we'll work up to harder ones. And we're basically going to be practicing. I got 12 questions for you for the rest of this hour. And these are all important and good. I picked them on purpose because I know they're things you need to know how to do. Okay? All right, so here's question 1. I would ask that you do write these down and leave yourself plenty of room to work them. Okay? Because if you just write the problems down and leave no space, how are you going to do them? All right, so here's your first one. 1 over tangent theta, sine theta, and cosine theta. And the problems always will say what it's supposed to equal. We don't like just say simplify that, because there's a lot of things you could simplify it to. But they'll always say what it should be. This one will turn into cosecant squared. So the first thought would be, okay, I guess I need to replace something with, well, I could replace tangent. That's the one he keeps talking about being a big deal. And then things will start canceling, and then hopefully you can simplify it down. All right, so then I'm going to give you a problem to, again, leave yourself plenty of room to work. And that's secant theta times cotangent theta times sine squared of theta will all simplify down to just cosine theta. Okay, start with those two, work with your partner, simplify them as quick as you can. Okay, in order to get done here, I need to get going. Tangent is sine over cosine. And then the sine and the other sine will turn into sine squared. And this cosine will cancel. So really it's 1 over sine squared. Oh, and that happens to be cosecant squared equals, bring that one straight down. Raise your hand if you guys had that one right. Okay, cool. Neil, did you guys get that one right too? Okay, all right, now you know. All right, on this one, on number 2, secant is, right away I'm thinking, go with the sister function, which is 1 over cosine, times cotangent, which is cosine over sine, and then those cosines are just begging to cancel each other out. But wait, I got to do this sine squared on top. And if you're like, that doesn't have a denominator, just put a 1 on the bottom. And now that and that will cancel, and there's 2 sines over 1 sine. I know they can cancel, but I'm just going to show you sine over sine, and it makes it really obvious that they cancel, and it's just sine. Okay, I'm freaking out a little bit. Is this actually equal to sine? It's supposed to equal cosine. So what's going on? Either A, I did it wrong, which is possible, or B, the problem was set up wrong. Pausing for a second. So if you were stumped on that one, it's probably because I think the problem was wrong. I think it's equal to sine. So I apologize. I will make the changes in the notes. That was a flawed problem. If you proved it was equal to cosine, that's impressive, because I don't think it is. If you really think it's equal to cosine, could you tell me where to go from here? Okay. I think I just goofed up the problem. Made me think that if somebody figured it out, yay, maybe the problem was right and I'm just doing it wrong. All right, moving on, number 3. On this one, I'm telling you up front that you're going to want to use conjugates. And at least one of the 2 people in the group hopefully knows what a conjugate is. Equals 1 plus cosine theta over sine squared theta. So when you use conjugates, you do that to the one that looks like this. That's where you're going to do the conjugate. All right, so let's see if you have learned how to do this well. Otherwise, I will be explaining it in a moment. Go ahead, give it a shot with your partner. All right, the conjugate is 1 plus cosine. It's as simple as that. But the magic that happens when you multiply on the top and the bottom by the conjugate is that the bottom becomes 1 minus cosine squared, which should ring a bell. That's right off of the sheet. 1 minus cosine squared is actually equal to what? Sine squared. The top here is 1 plus cosine, and the bottom is just sine squared. And now I've got the exact same thing I was trying to prove. It's right there. It's a little messy, but any questions? Okay, next one. This one, I will tell you, involves factoring. Sine theta plus 1 over 1 minus cosine squared of theta. And I think I actually screwed this up. I apologize. It's cosine up top. Cosine theta plus 1. And this will equal 1 over 1 minus sine. Nope, cosine. Dang it. I changed the problem partway through and it messed me up. The very last thing is cosine. All right, give that one a shot. Side note, in case you're stumped, Remember, if you can factor it, you should. This part right here gets factored. Okay, so here, hopefully you factored it, and now this and this can cancel, and you're left with 1 over 1 minus cosine. Who was able to get that far without me? Okay, awesome. Then number 5. Number 5 looks scary, but it is not. But write this out fast. Sine theta, tangent theta, cosine theta, plus cosine theta, cosine theta. And by the way, it says it at the beginning, it's equal to 1. This will simplify to 1 if you do it right. Okay, so can you figure out how to prove that that's equal to 1? Remember, you're going to keep that simple side the same and just keep replacing things and simplifying it down. All right. Once again, I said this would come up probably more than any other thing. Tangent is sine over cosine. And then this this cosine will cancel this cosine. Sine squared plus cosine squared. And what is sine squared plus cosine squared? 1. 1 equals 1. All right, on to number 6. Number 6 is tangent theta plus secant theta is equal to 1 plus sine over cosine. The hint I want to give you on this one, you have 2 separate things and you want it to combine into one fraction. So get it to have common denominators on this side. Make it so they have a common denominator. And then it's easy peasy. Okay, pausing for a second. Okay, so once again, tangent gets replaced with sine over cosine. Happens a lot. And what I'm left with is sine plus 1, but I'm going to switch that to 1 plus sine because I want it to match the other side exactly. And there we go. Look at that. Bring this down. There we go. Okay, on to number 7. Number 7, I'm pulling the plug on number 7. It's brutal. We'll get through a lot more if we skip number 7. I'm going to go to number 8. And this is long but easy. Sine theta, tangent theta, secant theta, cosine theta, cotangent theta, sine theta. I know it seems ludicrous. Plus 1 over secant squared. And it all adds up to 1. Prove it. Okay, I bet you noticed that tangent and cotangent would cancel each other out. Because tangent is like 1 over cotangent, and so they'll just cancel. And secant and cosine will just cancel each other out. And then sine times the sine makes sine squared, and what's that one? 1 over secant squared? That's cosine squared. Sine squared plus cosine squared equals 1. Do you get how this one and this one together make sine squared? And this one's cosine squared, sine squared. Plus that one, cosine squared, equals 1. 1 equals 1. All right. Raise your hand if you got that one. I'm getting the weird vibes on this one. Okay, I think it was just too easy. All right, on to number 9. Negative sine squared theta plus 1 minus 1 over cosecant squared theta. And that little nugget right there, you're going to want to change that to something else. Prove that that's all cosine of 2x. You might have to look it up on the chart because I don't know if you know what cosine of 2x is supposed to look like. But my hint for this one, right here, change this to the obvious thing, and then look it up on the chart. You probably don't have this one memorized. So I should have made this last x into a theta. But anytime you see an x and a theta, they can be swapped for each other. They're just a variable. Okay. So this one, 1 over cosecant, that's sine squared. And this is another sine squared. But this is negative sine squared, and this is negative sine squared. That makes negative 2 sine squared. And then I have that 1. That 1, I'm going to choose to put it in the front, and it'll be 1 minus 2 sine theta. Did you see that on the sheet? Because right on the sheet, it says 1 minus 2 sine squared theta. I'll show you. It's the middle one right there. Okay, so you could have then replaced that with cosine of 2x, because it's right off the sheet. Cosine of 2x, or a theta, equals cosine of 2 theta. All right, number 10. Realistically, probably the last one we'll get to. Sine theta over 1/2 secant theta. Show that that simplifies to sine of 2 theta. I'll pause for a second while you give this last one a try. Okay, we made it to the last one for today. Hopefully you knew that when you divide by 1/2, that's the same as timesing by 2. Okay, and then, so now I have 2 sine theta, and that really looks close to 2 sine theta cosine theta. And then the secant is still on the bottom, though. It would have been too much to try to do it all at once. So now I got 2 sine theta over secant is really 1 over cosine theta. And then when you have a fraction over a fraction, this can be flipped and multiplied, and that makes 2 sine theta times cosine theta, and that's exactly what sine of 2 theta is, right off the sheet. But you don't leave it that way, you finish with sine of 2 theta equals sine of 2 theta. All right, we made it. I do have more questions, but I'll save them for a different day because I think you worked hard enough. And you've now seen the entire sheet. Do you get that our test is on Wednesday? That leaves us 2 more days to review. You're going to get better and better by doing more practice problems, and then test on Wednesday. So please, please tell me that you're going to do a few of the homework problems over this weekend. I know you think that you'll be fine without them. I'm warning you, tough test. Okay, that's all I got for you for today.